model it up. That's how I'm gonna spend most of my next time it. So I need to model the attraction force and the repulsion force. First, let's do it for the attraction force. So at any general point, let us say Q is where my robot is, any general point of time, and that is the goal. So first, I am now being formal. I'm dealing with electrostatics, so I'll model the potential first, and then I'll model the force. So potential is a scalar and its derivative is the force. The force acts because of a differential of potential. That is when particles try to reach a lower potential value and therefore they move in the direction of the potential change. So I'll first model the potential and then I'll model the force. So potential will be denoted by U and force will be denoted by a F. So I say U, attraction towards the goal, is equal to, and let us say it's K attraction, distance between Q and goal square, and because I'll be taking a derivative, so let's take half over here so that it cuts each other. So this modeling is the one which is called as a quadratic potential, and the force is a derivative of it, so take a derivative of and it goes to reduce it, so the negative sign. So this will be given by 2 and 2 cut each other, K attraction, dq comma g. Now it's a vector. So why is it a vector? Because the distance between Q and goal is a function of the x and y component of this Q. It's a function of this Q, and Q has a x and y component. So when I take a derivative, even though it appears that I'm taking a derivative across distance, I'm taking a derivative across this value which has x and y components, so I'll get a vector, and therefore let me denote it as minus derivative of the q comma g, and if I need to reduce the distance, if I need to increase the distance between Q and G, which direction do I follow? I use this direction. So if I go here, the distance will reduce at some speed. If I go here, the distance will reduce at some speed. If I go here, the distance will increase at some speed. If I go here, the distance will increase at some speed. If I go here, the distance will increase at the maximum speed. So if I want the largest derivative of this thing over here, which direction do I move? That is in this direction, so that is Q minus goal. And I need to make it a unit vector, so distance between Q and goal. So this is what's called as a unit vector, the vector divided by its magnitude, and this is the magnitude of the force and this is the direction of the force. And therefore it's called as a quadratic potential, where the potential function is proportional to the square of the distance, and therefore the force is linearly proportional to the distance. Now many people will be cutting this and doing another step. That's perfectly okay. Distance and distance cut each other. So when simulating, you know this vector, this is given as an input. Every agent knows its goal no matter what. You know the position using techniques not discussed. So this is the relative position of the agent with respect to the goal, and K attraction times is the magnitude of, is the force. The magnitude, it's still linearly proportional because here this was the unit vector and now this is the actual vector. Now the problem over here is the force is proportional to the distance value. So let me write down here which means that especially during this pandemic, when you are somewhere and the person whom you love is somewhere miles and miles away, this force becomes so abruptly large that you want to throw away everything and just go running, which is pretty bad. So the problem is that the agent at many times will be far away from the goal. You know where you take classes and you know where you start from. Many times you'll be far away from the goal. You want to go to the market, you are far away from the goal, and this value becomes so large. So, of course, what I do is I apply a limit, and beyond this limit, the force value will never be considered. So, that's what I'm going to do here now. I'm going to apply a limit, and I'll have a fancy way of applying the limit. I'll say that let's model in another potential. So U attractive G. This time I'll go quickly, and I'll say that it is K attraction dq comma G. So this was quadratic. There was a square term involved. This one is called as conic, directly proportional. Force is the derivative of the attractive force. I'll write that down over here. So derivative of distance with respect to itself, the attraction. However, I need to take a derivative with q. So of course the derivative of distance, and it will have exactly the same vector. So it's q minus goal divided by dq comma goal. Don't say that the force is inversely proportional to distance. This divided by distance is to make this a unit vector. The force is constant, so you see the force is constant over here. Now I've got two ways to model an attractive force, a quadratic and a conic, and because of that, let me plot in the two as well. I'm only plotting the magnitude and not the direction. Oops. So this is the distance between Q and G, and this is the force attractive towards goal, the magnitude only. So in this one, what happens is, that's a conic. The force is constant, and in this one what happens, the force keeps on increasing. So this is quadratic and this is conic. Now which one is better? Let's find out. The problem with this one is that it's too large, far away from goal. So it becomes problematic, too high value. So when we simulate it, actually you see the robot colliding with obstacles because the attraction force is that large. The problem with this is that it is not zero at goal. So when you simulate it up, what happens is, this is the goal. The robot will come around over here with a constant force value. It's so close to the goal, it still has a constant value, and as a result, it will overshoot the goal. And then the direction of the force changes to here. As a result, it will again overshoot the goal. It will again overshoot the goal. So it's found oscillating to and fro from the goal because it's not zero at the goal. Here, what happens is that far away it's high, then it reduces its speed, it further reduces its speed, it further reduces its speed, it's almost zero and it's actually zero. So it stops nicely at the goal. That's what you see as well, that this is exactly what you would have used as a P controller. The velocity is proportional to the error. So a P controller is naturally embedded over here. Here what you see is it's just constant, so it's a Bagman controller. So it just looks at the direction and shoots with a constant step in that direction, and a P controller is definitely better. Now, it turns out you don't have to make a choice because This is better near goal. P controller, it will stop smoothly at the goal, it will start reducing its speed near the goal, and it's worse away from goal. And this one, it's better far from goal, and it's better worse near goal. And therefore what we do is we fuse the two up. So let's say hybrid U attraction goal is equal to if dq comma g, it's away from the goal, near goal, and else now there's one problem over here. Even though what you see is absolutely correct, it's a potential function and its derivative is the force, and from mathematics you know that across the attraction the value needs to be continuous and it needs to have a derivative. So if I just make a correction so that half k attraction d attraction square is equal to k attraction d attraction, and because of this, so I'll have to multiply with the d attraction to make it equal, and it's still half, and I also need to make the derivative correct, so I'll have to subtract with half its value. So this little thing that I did right at the end was just to make sure that the derivative exists at the point of discontinuity, and I mean at the attraction, and there's no drop in continuity at the attraction. So along with that, what will happen is that it will be quadratic at smaller values where it was better, and it will be linear at larger value what is better. And the force, of course, is again exactly the same thing. So let me write it down directly. So it's minus k attract q minus g divided by dqg into dqg. So cut if dqg is less than equal to d attract, and if dqg is greater than d attract. So you take a derivative, this will become a constant, that's a good thing. So it's just d attract k attract q minus g by dqg. So the forces, the hybrid force happens to be the best thing. So till the attract, it goes linearly and then it becomes a constant. So that's your quadratic and that's your conic. Simple behavior, nothing much to say about it. Normal modeling of the forces, and that's your easier of the two forces, which is the attraction and repulsion towards the force. Now it turns out that I have another force, which is the repulsion force, so let us model for the repulsion force as well. This time what I will have to do, unfortunately, is I take a Q and I take in one small point obstacle O. So we'll increase the shape and size of the obstacle and we'll have many obstacles later upon, but to start off with, let us take this thing as a value. So I say first let's do it for the potential. It's repulsion. So the repulsion force as a result of a point obstacle O. So this is equal to, again because I have to take a derivative, k repulsion 1 upon dq comma O. the whole square. Okay, now there's a problem over here. Now the problem over here is that I said previously reactive decision making, we only take entities which are within the proximity. And that's exactly what it does. It effectively takes entities which are within the proximity, because afterwards what will happen is this d will become so large and 1 upon d will become so small that it will virtually become 0. And therefore your entity, your simulated entity, your agent, your robot is effectively only looking at the nearby elements and it's deciding what to do when. However, there probably is a problem if a mathematician looks at this and the mathematician say, I need a formal proof that the thing that you are saying is small, it doesn't affect. Maybe 1 upon d and 1 upon d, some other d cut each other, and what you're calling as small becomes large. So mathematicians need a lot of formalism. So let us manually make a force of 0 for all entities which are far away. You honestly don't need to implement it up. It'll automatically become 0. It'll become that small. So I say is greater than d rep. I can actually do this. So if dq comma o is greater than d rep. So that's again where proximity query comes in. I'll only look at entities which are around d rep, and the entities which are around d rep are the only ones which I'll consider for my decision making. K nearest neighbors, all neighbors at a distance of d rep. And if it goes beyond that, I'll manually make it 0. Again, you need to make sure that it's derivative free. I mean, it has a derivative and it has a continuity. There you go. So that's my repulsion force. Pretty much what you would have imagined. And my force due to obstacle O is equal to, take 2 and 2 cut each other, so it becomes k rep 1 upon dq comma O minus 1 upon d rep. And then I'll have to take a derivative of this. So derivative of 1 upon dq comma O with respect to q will become minus 1 upon d square q comma O. And then with respect to d itself, so this was with respect to dq comma O. Now I'll take a derivative of dq comma O with respect to q. So this will become again the same term that we've had a look at previously. And in the other case, of course, it will be 0. And if you look at it, this becomes cube, and the minus minus cut each other. Oh, it's minus derivative. So this becomes 0 k rep 1 upon dq comma O minus 1 upon d rep. Minus and minus will cut each other. dq can be combined into 1, so it becomes q minus O divided by dq q comma O, where it's actually inverse to the square over here because of this term. There's another term over here. The 1 divided by dq comma O is because this is a unit vector, so this one is actually a unit vector. And that's my repulsion force. With respect to a point obstacle O,